It's really fascinating, how echoes from the past can resonate today, like Henry Ford tinkering with pure ethanol.
Hmm.
And then you have Rudolf Diesel, the inventor, right? Originally planning for his engine to run on pure vegetable oil.
Absolutely. It really highlights this long-standing connection between agriculture and how we power things. Diesel saw it as a benefit for farming, specifically.
That basic link, farming and fuel, it feels like we're circling back to it now, doesn't it?
We really are, yeah. With a new sense of, well, urgency.
Okay, let's dive into this. Today we're doing a deep dive into Lecture 9 of Professor Ghosh's Renewable Energy Resources course. It's from ICT Mumbai, and you can find the whole thing on YouTube.
Right. In this lecture, number 9, it really gets into bioenergy, specifically biodiesel, and then starts laying the groundwork for solar energy.
We're going to pull out the key insights from Professor Ghosh's lecture, make them hopefully easy to grasp, maybe spark a few aha moments, without getting bogged down in all the technical jargon.
Yeah, think of us as guides through his expert knowledge. We want to spotlight the most compelling bits.
All right, let's jump into biodiesel then. Professor Ghosh kicks off by reminding us, like you said, diesel's initial idea was neat vegetable oil.
Right.
But that didn't really work out for the later high-speed engines. The oil was just too thick, too viscous, and the fuel injection nozzles were too fine.
That's a key point. Engine tech kind of evolved away from pure plant oils initially. But what's interesting is how biodiesel is making such a comeback now.
Why now?
Well, mainly because of the urgent need to tackle vehicle emissions and pollution. Environmental concerns are huge drivers.
Right. And Professor Ghosh links this to the big net zero targets, the US, UK, EU aiming for 2050.
Exactly. And biofuels, like biodiesel,
Hmm.
they're seen as pretty essential tools to help hit those targets. Transportation is a massive chunk of emissions.
So it's about cutting the carbon footprint.
Fundamentally, yes. These net zero goals mean we have to seriously transform our energy systems. Biofuels are one promising path away from fossil fuels.
And for India specifically, Professor Ghosh mentions another big motivator alongside the environment:
Which is,
reducing dependence on fuel imports, using their own agricultural resources to boost energy independence.
energy security. That makes sense. For a country with a strong agricultural base like India, biofuels offer a way to use local biomass for fuel, strengthens resilience.
Now, that term net zero, it can feel a bit, I don't know, vague sometimes. I like how Professor Ghosh used a specific example, a Jatropha plantation, to make it clearer.
His breakdown of the carbon cycle in that context is really helpful. It's not just about the fuel itself.
Right. He talks about how the plants, the Jatropha, pull CO2 out of the air through photosynthesis. That's the carbon sequestration part. And the carbon's stored not just in the oil, but the whole plant.
But then, and this is crucial, he gives a reality check. He doesn't just focus on the capture side. He details all the CO2 emissions linked to making the biofuel.
Yeah, he lists everything. Burning leftover biomass, leaves rotting, even insects breathing.
Right. And emissions from making fertilizers, pesticides, running water pumps. It's the whole picture.
It gives you that complete carbon balance sheet, doesn't it?
It does. And his point is you have to look at the entire footprint. You can't just count the CO2 the plants absorb. You need to subtract all the emissions from production to see the net effect.
And that's the core of net zero, really, getting that balance right between capture and emission. He warns against bluffing the numbers. Transparency is key.
Absolutely. It underscores why rigorous science and honest accounting are so vital. No shortcuts to true net zero.
Okay, so the biodiesel we actually use today isn't just raw veggie oil. Professor Ghosh gets into the science. It comes from triglyceride oils.
Yep. Think of them as big, complex fat molecules found in vegetable oils, animal fats.
And the problem with using them raw in modern engines is still that high molecular weight and viscosity.
Exactly. They're just too thick, too heavy.
And he mentioned someone named Water in England who first thought about breaking these big molecules down.
Yeah, into smaller bits fatty acids. That was a key early idea. Break them down, reduce the viscosity.
Makes sense. But as Professor Ghosh clarifies, we don't run engines on pure fatty acids.
No. Modern biodiesel is actually fatty acid methyl esters, or other esters. They've basically converted those fatty acids into something more engine-friendly.
And glycerol is a byproduct of that conversion.
Right. That chemical tweak makes a big difference in fuel properties for diesel engines.
Now, the history part here is really cool. Professor Ghosh points out that transistorification, that core reaction to make biodiesel, it's not new tech at all.
Not at all. It was known way back in 1853. That's even before the diesel engine was invented.
Wow, so the chemistry was there, just waiting for the application.
Pretty much. The challenge was applying it to make a practical fuel for this new engine type.
Then fast forward to 1937, a Belgian patent. First description of making these esters specifically for vehicles using palm oil.
And get this, in 1938, they actually ran a bus on it, an early trial. But it shows the concept was there decades ago.
Surprising it didn't catch on then, but he credits researchers in South Africa for really refining it later.
Yes, they focused on cleaning it up, removing impurities, making it more reliable for engines. That was critical work.
Okay, then 1987, an Austrian company, Gascox, licenses the South African tech. First commercial plant using rapeseed oil.
Rapeseed, which is edible oil. And Professor Ghosh notes that even then, people raised concerns about using food for fuel.
That whole food versus fuel dilemma, it's been around a while.
Definitely. It's a constant balancing act. Energy needs versus food security.
So by 2003, Europe's leading production, over 1 million tons. The U.S. was a bit behind then, he mentions.
And because Europe was pushing it, their car companies, like VW and Mercedes-Benz, got heavily involved in R&D.
Which leads us to Professor Ghosh's own institute, CSIR, in India. Around 2003, they started this project with Mercedes-Benz.
Yeah, this was huge. A world first, actually.
What was the first?
Mercedes demonstrated running standard, unmodified diesel engines on neat Jatropha biodiesel. 100% biodiesel.
Wow, 100%, not a blend.
Nope, pure biodiesel. Before that, everyone pretty much assumed you needed blends or engine modifications.
And the key was using Jatropha.
Exactly. It's a non-edible oilseed. And crucially, it can grow on marginal land, wasteland, so it sidestepped that food versus fuel fight.
That seems like a massive breakthrough, non-food source, standard engine.
It really was. And Mercedes wasn't just doing a lab test. They were interested because Jatropha didn't compete with food crops for land.
Makes sense. Then later, 2008, Air New Zealand flew a 747 on a blend.
Right, a 50-50 blend. Professor Ghosh is careful to say it was a different type of biodiesel, though. We'll get to that. But it showed potential for aviation, too.
The lecture even shows pictures of this really arid, rocky land where they grew the Jatropha successfully.
Yeah, it drives home the point about using otherwise unproductive land. These plants are tough.
And this work got recognized in Nature magazine.
It did. Put India's biodiesel work on the global map. There was even a German TV documentary about the whole thing, from graying Jatropha to running a bus on 100% biodiesel.
So this wasn't just a proof of concept. This Jatropha biodiesel had to meet strict fuel standards.
Oh, yeah. Very stringent specs. And it met or even exceeded them. That's what gave Mercedes the confidence for that 100% run.
And another interesting point, the high flash point, around 140, 150 Celsius.
Right. Much higher than regular diesel, makes it significantly safer to handle, less risk of accidental fire. He even mentioned it didn't fall under the Petroleum Act rules back then because of it.
That's a big safety benefit. And before hitting the road, lots of testing.
Extensive testing. Daimler Chrysler India, ARAI in Pune. They checked everything. Fuel consumption, all sorts of emissions. CO, hydrocarbons.
Yeah.
No NOx, particulate CO2.
Thorough. And the chemistry they use base catalysis with KOH, potassium hydroxide?
Yes. They looked at acid catalysis too, but base catalysis was simpler. Could be done at room temperature. More practical.
So, April 5th, 2004, that first historic run, and then they really pushed it. Pune to Delhi.
Pune to Delhi, yes. And even drove Mercedes cars up to the highest motorable road in Leh, all on 100% biodiesel, exceeding Euro 3 emission standards even way up there.
Incredible, real-world, extreme conditions.
And an independent Austrian study compared it favorably to European biodiesels. Better torque output. Professor Ghosh proudly calls it the world's best biodiesel, based on that.
And it wasn't just cars, buses, military vehicles, even international interests.
Yep, buses, military trucks, the crown prince of an emirate even came to see the work. It showed real versatility.
Professor Ghosh makes a point, though, that while the basics oil, methanol, catalysts sound simple,
the devil's in the details. He stresses there were lots of underlying complexities, process details that others missed when trying to replicate it.
Right? It's not just mixing stuff together. And he has that amazing story about the Toyota engine.
Oh, yeah. Dismantled after 163,000 kilometers on 100% biodiesel. Found it was incredibly clean inside, almost like new.
That's powerful evidence of the fuel quality.
Definitely. And applications went beyond road vehicles, stationary engines, earth-moving equipment, plus exploring waste cooking oil from places like McDonald's, Pepsi Frito-Lay.
Turning waste into fuel, great idea.
But he also mentions that frustration, the time lag in adopting new tech, how pioneers sometimes get shortchanged.
Yeah, that's a common story in innovation, unfortunately.
Okay, so how do they make this world's best biodiesel? The process details sound fascinating.
Right. He walks us through it. Starts with harvesting the Jatropha fruits, getting the seeds out,
Then pressing the seeds for oil.
and the leftover cake. Great manure. Closing the loop.
Nice. And even the shells and sludge weren't wasted. Used as a binder for briquettes.
Exactly. Potential fuel for biomass gasifiers. He also stresses processing seeds quickly after harvest.
Why is that?
To keep the free fatty acids FFAs low, high FFAs cause problems.
Ah, okay. And the process was good at reducing FFAs.
Very good. Down from like 2.6% in the oil to under 0.3% in the biodiesel. He also mentioned Jatropha oil has a good fatty acid mix and no phospholipids, which helps engine performance.
So the feedstock itself had advantages.
Yeah.
And the process was patented.
Yes. First step. Neutralizing those FFAs with a controlled amount of alkali, sodium hydroxide, carefully done to avoid turning the good oil into soap.
Clever. And the small amount of soap they did make.
That soap cake byproduct was used for making actual soap in villages. Really resourceful.
That's fantastic. Okay, so after neutralizing FFA,
Use a centrifuge to separate the soap cake and oil. Then dry the oil thoroughly with air.
get the water out.
Right. Then comes the main reaction. Transesterification. Mixing the oil with methanol and the KOH catalyst. Using about 1.5 times the theoretical amount of methanol needed.
Precise ratio. Got it. Then purification.
Crucial step.
Glycerol.
Glycerol washing. They add some glycerol back after removing the main batch. It helps pull out leftover impurities, methanol, catalyst, traces of soap, mono, and diglycerides.
Interesting use of the byproduct itself for washing.
Yeah. Then a final water wash, which works well without forming messy emulsions because of that glycerol pre-wash.
Okay, that sounds like a key innovation. Then drying again.
Final drying with dry air down to very low moisture, less than 500 ppm, and the overall conversion rate was high, around 95%.
Very efficient. What about the main byproduct, the glycerol?
Also utilized. Vacuum distillation recovers the methanol from it. Neutralize it with sulfuric acid, you get potassium sulfate fertilizer.
Wow, fertilizer too.
And get this, Dr. Sandhya Mishra discovered they could convert the crude glycerin into bioplastic using marine bacteria.
Bioplastic from glycerin. That's incredible.
Yeah.
Really closing all the loops.
Totally. And we did a full energy balance, too. Looked at all inputs, manpower, irrigation, fertilizer, transport versus outputs like biodiesel and briquettes.
And the result?
Energy output was about 5 times the energy input. Very positive energy balance.
That's essential for proving sustainability.
Yeah.
Okay, so Jatropha was a success story, but Professor Ghosh also talks about not putting all your eggs in one basket, right?
Exactly. Diversification is key. He warns against over-reliance on one thing, like sugarcane for ethanol.
So what other options did he mention?
For ethanol, things like seaweeds, lignocellulosic biomass, like agricultural waste, even rotten crops. For biodiesel, the search for oil-rich microalgae.
Algae. The next frontier, perhaps?
Potentially. Marine microalgae specifically. Oil content might be lower than Jatropha, but you can grow them in salt pans using seawater, not competing for freshwater or farmland.
That's a big advantage. And India actually ran a car on marine microalgae biodiesel.
World first, apparently. Collaboration with General Motors showed it could work.
How did it perform?
Reportedly smooth, comparable to regular diesel, no hiccups. They also looked at using the whole algae biomass, not just the oil, amino acids, other stuff.
Full utilization.
Yeah.
Makes sense. Did they analyze the algae biodiesel itself?
Yeah, from Chlorella oil.
Yeah.
It's mostly similar properties to other biodiesel, maybe a slight difference in phosphorus. But again, thorough testing is key.
Okay, but standard biodiesel, these methyl or ethyl esters, they have limitations, right?
Yeah.
Especially for planes.
Big limitation, cold weather performance. The cloud point where it starts getting waxy is only around -2 to -8 Celsius.
Not nearly cold enough for a high-altitude flight where it can be -40°C.
Exactly. So for aviation fuel, you need a different process. Hydrotreating.
Hydrotreating, what does that involve?
It's a different set of chemical reactions using hydrogen. Things like decarboxylation, decarbonylation, removing carbon and oxygen, plus hydroisomerization to make branched molecules that stay liquid at low temps, and hydrocracking to get the right molecule sizes.
So, same starting materials, maybe vegetable oil, algal oil, but a totally different chemical pathway to get jet fuel instead of standard biodiesel.
Precisely. Different chemistry for a different, more demanding application.
Okay, that makes sense. Tailoring the fuel to the need.
Right. So that pretty much covers the deep dive into bioenergy and biodiesel from Professor Ghosh's Lecture 9.
Really comprehensive look.
And then the lecture shifts gears. He starts introducing solar energy. setting the stage for the next few sessions in his course.
A logical transition from biomass to direct sunlight. How does he start with solar?
He begins with solar radiation reaching Earth, explains the sun is like a black body about 5,800 Kelvin, emits a whole spectrum of radiation.
But the spectrum changes as it comes through our atmosphere.
Exactly. Gases like ozone, water vapor, CO2, they absorb specific wavelengths. That's why the spectrum hitting the ground looks bumpy. Those dips are where the atmosphere absorbed energy.
Understanding that ground-level spectrum is key for solar tech, right? Knowing what energy is actually available.
Totally. Then he goes into the Earth's overall energy balance. On average, about 342 watts per square meter hit the top of the atmosphere.
And some gets reflected straight back.
Yep, about 107 watts per square meter bounces off clouds, the atmosphere, the surface, back to space.
The rest gets absorbed by the surface, heats things up, drives evaporation, makes clouds.
Right. And the Earth radiates energy back out, but at longer infrared wavelengths.
And that's where greenhouse gases come in.
Yeah.
They trap some of that outgoing infrared heat.
Exactly. The whole greenhouse effect mechanism. He notes it was Nobel Prize-winning physics, understanding that climate connection. But ultimately, energy in equals energy out for a stable climate.
So that balance is critical. Okay, what else did he introduce?
The air mass coefficient, AM.
Air mass. What's that?
It's basically a measure of how much atmosphere the sunlight has to travel through to reach you compared to if the sun was directly overhead.
So it depends on the sun's angle in the sky.
Exactly. Depends on time of day, season, your latitude. AM equals L over L0, the actual path length divided by the shortest possible path length, straight down.
Okay, so different AM values represent different conditions.
Right. AM0 is the spectrum outside the atmosphere for satellites. AM1 is sun directly overhead at sea level.
And AM 1.5, I hear that one mentioned a lot.
Yeah, AM 1.5 is a standard reference. Represents the spectrum at a typical sun angle for many populated temperate regions. But he also notes that things like humidity, ozone levels, dust, atmospheric turbidity affect the mix of direct versus diffuse light, even at the same AM value.
So you need standard atmospheric conditions defined for AM 1.5 to compare solar devices fairly.
Makes sense. So yeah, that intro to solar radiation and air mass really sets things up for the next lectures.
A good foundation. So wrapping up, we've gone deep into biodiesel, from its history to making it from non-edible stuff like Jatropha and even algae, with the energy balance, diversification.
And then just started scratching the surface of solar energy radiation, atmospheric effects, air mass. It's amazing how these different renewable paths work.
Professor Ghosh's lecture really ties together the science and the potential, doesn't it?
It really does. Isn't it wild how ideas from like over 100 years ago are suddenly so critical now, and just the sheer potential of capturing sunlight.
Absolutely.
His full Lecture 9 has even more detail, lots of visuals. We definitely recommend checking it out on YouTube.
If you want the full picture, the lecture itself is the place to go. Great expert insights.
So a final thought to leave you with. Thinking about that biofuel energy balance and the constant flood of solar energy hitting us, what other maybe unexpected ways can you think of to power our future sustainably? What resources haven't we fully tapped into yet?
That's a great question. What novel ideas or untapped resources might hold the key? Definitely something to ponder.